Well, good morning, everybody, and welcome to the first of today's webinars from Smart Vision Europe. And in this first webinar, we're talking about interpreting significance tests. And my name is Jarlath Quinn. I'm an analytics consultant with Smart Vision Europe. If you don't know who we are, we're an organization that's a technology organization specializing in analytics. I'll introduce this in a wee bit more formally in just a few minutes. But to begin with, normally when we run these webinars, we have a sort of housekeeping or FAQ slide at the start, just so that people are aware. First of all, the sessions are all recorded, so you'll get a link to the recording afterwards, and you can share that with friends, etc. There are lots of slides here, and we'll email out a PDF copy to you of the slide deck after the session's ended. There's a little bit of demonstration just for illustration purposes. With regard to arranging a rerun for colleagues, we do sometimes do that. You know, if you've got colleagues that aren't able to attend and you want to do a live session, the best thing to do is just to send us an email, something like that, and we'll see if we can get enough people together. We can usually arrange a rerun. It's not a problem. And lastly, most importantly, with regard to asking questions, well, all the lines are muted, so we can't hear you, and I won't be able to hear you. You can use the chat facility, and Rachel will try and monitor that. My colleague Rachel Clinton's online here, making sure everybody's logged in correctly. So she monitors that while I'm chatting through the slides and talking about whatever the subject is that we're covering in that particular session. But more importantly, we usually get a bunch of emails afterwards from people. So don't be afraid to just drop us an email if you've got questions, which we would expect lots of people have questions. And then we just work through those emails after the session's ended, and we're quite happy to open up a discussion and deal with those queries. Again, Smart Vision Europe, we are, as I say, a technology organization. We're quite a small technology company. We specialize in what we describe as predictive analytics, which is basically statistics and data science and AI and machine learning and all that type of stuff. We're actually a premier accredited partner at IBM and a company called Predictive Solutions. We all have a kind of common background in that we were all senior members of the SPSS UK limited company. If you know who SPSS are, they're a statistics company. So we've all worked for SPSS for a very long time. And I personally worked as a consultant and instructor and manager for SPSS and a company called SAS, if you were SAS, or an IBM and Smart Vision for the past 25 years. So we're very well versed in talking about all things statistics and writing training courses and running training courses. We have tons of YouTube videos and lots of materials on our website devoted to particularly subjects like this, how to interpret significance tests and the basics of statistics, right up to text mining and machine learning and that type of stuff. So we're all pretty experienced in that. We also work with open source software like R and Python and Spark. And our experience is spread across many different sectors of applying analytics. And it's really difficult for us to talk about typical application, typical sector. It could be everything from healthcare to policing to, finance or telecoms, media, that type of stuff. We've got quite a lot of experience in FMCG and food manufacturing, stuff like that. So it's very, very broad. But what we're talking about today is, is the absolute fundamentals of what you call classical statistics, which is, this business of significance tests and what they mean and how you can actually correctly interpret them. What's the correct way to make sense of them? And that's what we're focused on. So first of all, we're going to start off with the term, just this term significance testing. Generally throughout this, in my head, I'm using the term significance testing with inverted commas because it's a problematic term, as we'll see. And then we're going to open that up into the world of inferential statistics and how that relates to significance testing, and also hypothesis testing and how they kind of link together. And we're going to talk about this business of p-values, which are probability values. And then we're going to look at taking a fairly simple test of significance, a chi-square test, and just basically taking it apart and saying, how does this actually work? how does it come up with this number? And then we're going to look at examples of, when something is deemed to be statistically significant, but actually isn't that significant in reality. And that allows us to introduce correlations. And finally, we're going to look at confidence intervals. And there'll be a little demonstration here of how confidence intervals are generated and how we can correctly report them, what kind of form of words we can use to correctly speak about them and interpret them. So the first thing is that significance is a very troublesome term. I think if a bunch of statisticians could get into a time machine and go back, they'd definitely try to remove that term from the literature. And it's simply because it's misleading. It's misleading because the term significance means something in general English language, but doesn't really mean the same thing in the world of analytics. And the person who's responsible for it is Ronald Fisher. So Ronald Fisher is kind of the grandfather, if you like, of what we call classical frequentist statistics. That's the stats that we're taught at university and at school and that sort of stuff. And you do a basic stats course. Most of that stuff is Ronald Fisher's ideas. It's underpinning it. So he introduced the phrase tests of significance in a book, almost as an offhand phrase, in a book called Statistical Methods for Research Workers, way back in 1925, so nearly 100 years ago. And unfortunately, saying that something is statistically significant is likely to be misunderstood. People use that as a justification, if you like, and say, well, it's statistically significant, as if that means anything. And it doesn't necessarily mean anything, because significance sounds like something is notable, and it's worthy of note, that you should pay attention to it. So not only is the term significance troublesome in that sense, but it doesn't even mean it's necessarily reliable. One of the issues in the world of statistics at the moment is something called the replicability crisis or reliability crisis. And you can actually Google that and look it up. And it's basically refers to the fact that if you look at a lot of classical studies that were done in the 1960s and 70s, particularly in the world of psychology and social sciences, when people have tried to replicate those studies, they find that they don't get the same level of significance, the same results, if you like, when they reproduce them. So there's an argument here that that just because something is given a probability value doesn't necessarily mean you're going to get the same probability value if you repeat it. And there are certain suggestions that are being made and movements, if you like, tectonic movements within the statistical world at the moment to try and address that. So it's an issue. The last thing is even the term test is problematic. When we think about the term test, we think about like a pregnancy test or a coronavirus test, or even like a smoke detector or something like that. And tests of significance are troublesome, because what we're ending up with is really an estimate, an estimated value that tells us how likely something is to occur, if you like. So it's not really a test in the sense it's sort of thumbs up or thumbs down, but that's how almost for generations students of statistics have been taught to interpret stats, is to say this is significant, that's not significant, as if it's sort of lighting up green or red. And it's an appalling situation, really, because that's not really the spirit in which these values are calculated. The more accurate definition, if you like, of a significance test, and it's one that I just sort of thought of, was if you were going to properly describe it, you'd say these are probability of evidence estimates, which I completely accept nobody's ever going to use as a definition, because it doesn't exactly roll off the tongue, but it's the closest thing you can get to what the test is actually, what these tests, if you like, are actually doing, is that they are giving us probabilities, and the probability is an estimate, if you like. It's a probability of evidence of something being true. It's an estimate of that. So when we start to take the whole thing apart, it's not quite what it appears to be at the start. Now, Ronald Fisher is not the only person that is responsible for the landscape, if you like, with that tests of significance or significance tests exist within. There's a bunch of them, but it's a relatively small number of people. So if you've ever had if you've been taught statistics in the past, you've done it at university, if you're working with statistical tests at the moment, if you're looking through manuals and Googling stuff to try and interpret different tests, you'll be familiar with many of these terms. These are the bread and butter terms that our courses are littered with things like confidence intervals and chi-square and null hypothesis and ANOVA and z-test and exact test and probability and f-test. F-test, the term f-test is a very common test. The F comes from Fisher, for example. The correlations are usually referred to as Pearson's correlations, come from Carl Pearson. So you're talking about four guys really here that are really responsible for the majority of the landscape, almost laying down the rules of what are called frequentist, the traditional statistics. So you have R.A. Fisher, you have Carl Pearson, you have Carl Pearson's son, just to show you how sort of nepotistic this is, Egon Pearson, and Egon Pearson's co-worker, Jersey name, and those two are responsible for things like confidence intervals, if you like. So it's interesting when you see it within that historical context that, you know, it's not necessarily a vast army of people where this has evolved over time. It's more that they have used terms and phrases that people have kind of picked up on. You should also be aware they didn't necessarily get on with each other. They didn't actually agree with each other. And a lot of the notions in classical statistics are to a certain degree a sort of fudge, where they've had to kind of agree to disagree or come up with a form of words. And as a result of that, you know, it's become tricky and difficult for students of statistics in decades, hence to get their head around it and figure out how it all fits together. And it's understandable in that sense. So let's get back to significance tests and focus on that. First of all, we need to understand what we mean by inferential statistics and how that relates to significance tests. Now, if you've done anything in statistics ever, if you've done any sort of training or anything like that in statistics, you'll notice that the one thing that people go on about in statistics is the difference between populations and samples. And it's not always explained to us why this is so important. So we're going to try and fix that here. A statistic is a calculation that comes from a sample, and a sample, of course, is exactly that, is when you dip into an ocean, if you like, and you pull up a sample and you take a measurement from that. The population is the ocean, and it's unknowable to a certain extent. The equivalent of a statistic in a population is called a parameter. And the parameter is usually a sort of unknowable value. So for example, if you wanted to know what the average age of people is in the UK at the moment, you actually don't know that. And nobody really knows that at the moment because there's always going to be some missing data. And if you wanted to calculate it to, like, 2 decimal places, in reality, the number is flickering and changing. So any sample that you take is a snapshot in time. So statistics are used to make inferences about parameters, about the true values, if you like, the true value in the population. And much of the significance tests are the business of trying to infer that. So hence the term inferential statistics is to infer what the true value is based upon our sample. Okay, so that's a theoretical background to it. So how do we do that? How do we infer a parameter value of a population from a sample statistic, particularly when different samples produce different results? If we were to go and sample the ocean and say, let's figure out the exact salinity of the ocean, you might find, I'm not an oceanographer, but you might find, for example, a pollution value or salinity value might actually vary from what part of the ocean or from each sample that you take or from the depth of the time of day or whatever. And you'll get slightly different values. So, for example, if we were taking a sample of, let's say, 100 or 200 cases from a population, said what is the mean age of men and women, we might find that as we repeat the sample, we get slightly different mean ages, slightly different average ages. You could even potentially get an average age where women are slightly older than men. So they vary from one another. And this is a critical concept, the idea of variation, because something which really isn't taught to us at university is a very important truth about statistics, and that is that statistics is the science of variation. So as soon as you start thinking of it in terms of estimates of variation and calculations of variations, rather than the science of discovering the truth, if you like, then it starts to make a lot more sense. It's about the fact that things vary, that samples vary from one another, and that there is variability within the sample itself. So there's variability between groups and within groups. And that's a very important concept that you see again and again, almost like a recurring motif in the architecture of statistics. So there's a science of variation. So for example, if we wanted to ask the question, what's the likelihood that the mean ages are actually the same in the population, we would need to do some sort of calculation to estimate that and say this is the likelihood of that being true. Why would we say that they are actually the same in the population? Well, why not? I mean, if you're finding that one age group, the women are actually older than one of the samples, the mean ages for the women is actually older than the men. Maybe in reality, the true mean age is that they're both 32 on average. Maybe that's the actual answer. So maybe all the differences that we're observing in our samples are simply a result of sampling error. So that's kind of important. And that helps us to start to form a sort of theory or to start to set up a statement for us to prove or disprove. So where does significance come from? Where does that come into it? Well, significance, as we say, doesn't mean that something is noteworthy. Instead, it says that if you were able to test this notion that in our example here, that the two means are in fact the same, if you're able to test it, then the results might show that the evidence doesn't support the assumption that there's no difference between certain groups in the population, or maybe the evidence does support the assumption that there's no difference between the groups in the population. Now, the way in which that evidence is going to be presented to you within a statistical package like SAS or SPSS or R varies according to the procedure that you're using. And that's another thing which is confusing for people, is that sometimes it will say something like SIG, sometimes it will say P, sometimes it will say prob, sometimes it has a label like asymptotic significance. Asymptotic just means estimated significance. You should almost ignore the label. The label's not important. It's just a convention that different people who've written different bits of software have come up with. The numbers are interpreted in exactly the same way. So when we see a sig value of 0.001, what we do is we convert that in our head into percentages, and we just multiply it by 100. So you just get used to shifting 2 decimal places kind of towards the left here. So that means a significance value of 0.001 means a 0.1% chance. Basically a 1 in 1,000 chance. A p value, a sig value of 0.172 means 17.2% chance. And very often you'll see p values that say 0.000. That doesn't mean there's no chance. It just means that the box doesn't have enough decimal places. It can't display all the decimal places. And it just means that the probability is very, very small. It's even smaller than 0.1%. That's all it is. It just means it's very small. Or sometimes you'll get like 0.034, which will come out like 3.4% or roughly 3%. So you get used to looking at these numbers and converting them into percentages. That's the first thing, and not to be thrown by these labels. Okay, so that's the first thing. Don't get thrown by these labels. But returning to this notion of significance tests, if we assume there is no difference or no relationship between the two groups, in fact, that mean average age for men and women isn't in any way significant or it's any way different from one another, we could actually calculate a probability value which would tell us, saying, well, if indeed there is no difference, and we're seeing a difference of 34 to 32, let's say, in the mean ages of, say, a sample size of 100 and, I don't know, a standard deviation of 15 years or something like that, it's saying that we would see a difference as big as this 11% of the time. That's how we would interpret the p-value. It's saying you would see a difference as big as this 11% of the time, even if there was no difference between the two groups in reality. So that's a clue right away here. It's not saying this is the probability that there is in fact a difference between the two groups. It's saying that, it's a bit like flipping a coin 100 times. You can't flip a coin 100 times and have it come up 80 times head and 20 times tails. And it's saying, well, assuming the coin's fair, what's the odds of getting that? Well, how often would you see a difference as big as that, between what you would expect to get, which is that there's no difference between the heads and tails, is 50-50, and what you actually got, which is, quite a big difference, 80 times heads and 20 times tails, something like that. So the p-value is simply telling you this is how often you would see a difference as big as that, assuming there is no difference. So here we've got a bigger difference, 33 to 30, and the p-value is much smaller. It's saying you'd see a difference as big as that 4% of the time. Or here is a quite very small difference, 31 to 30, and it's saying, well, that's quite a small difference, so you'd see a difference as big as that 33% of the time. And that's how we're using it. And in this case, the test that would be used to compare two averages happens to be a t-test. and they're used to compare mean values. But we're not going to go into the t-test and calculation of that at the moment. It just suffice to say that when we punch out these p-values, this is the framework. This is how we're thinking of them, saying how often would we see a difference as big as that, assuming there is no difference between the groups. So how does this relate to hypotheses? Because I'm talking about this idea of there being no difference. It's almost like this is anchoring us. How does this relate to hypotheses? Well, significance testing is often referred to as hypothesis testing. And if, of course, you're investigating a relationship with statistics, it's usually because you're curious to see if there's a difference or pattern. If you're recording people's gender, it's because you think it's important. If you're recording what region they're living in and you're asking how satisfied they are with service, you're assuming that maybe regions might be an important factor in that people might have different levels of satisfaction depending on the region. So there's always an implied hunch, if you like, that you're trying to test. So you've always got some sort of hypothesis in the back of your mind, even if you're not necessarily aware of it. And ideally, you should be aware of it. You should actually be saying it out loud. But for example, if you thought that there was a difference between the average age of men and women in your population might be, I don't know, people who are taking a service up, or people who complain, or people who fall under a particular group. Maybe it's a vulnerability group or something like that, or treatment population for a particular illness. That's called the alternative hypothesis. That's where you say, I think there's a difference. But what you're testing is you're testing to see if your data supports the idea that there is no difference between the average ages of men and women in the population. And this is called the null hypothesis. So when you calculate your test, when you use some software or something like that, calculate test, and it gives you a probability, the probability indicates that if the null hypothesis is true, how often would we get a result as extreme as the one we observe? So you can see I'm heading over the head of this again and again. The reason I'm leading up to that is because what we're not doing is we are not saying that it's the probability of the null hypothesis. Okay, so we'll come back to that in a moment. But what we have to focus on is, well, given the fact that we've got this number, we've got to say, well, of what threshold do we say whether or not there's enough evidence to support this null hypothesis? How big or small does the probability value have to be before we decide that the data doesn't provide enough evidence to support the null hypothesis? Maybe 32%, maybe 0.32. Does that seem a reasonable threshold? It's a bit of a weird number to choose. Maybe 100%. Maybe you have to say it has to be 100% chance that that the null hypothesis is true, or that there's a 0% chance that the null hypothesis is true. That's quite extreme, since you could easily flip a coin 1,000 times and have it come up tails every single time if you did it enough times. If you did it enough times, it could happen. It's just not very likely to happen. Clearly, we have to choose some sort of threshold. We have to kind of draw a line in the sand. In fact, this threshold is known as the alpha level, and it's fairly arbitrary. In other words, there's no real reason why you would choose this particular number. It was just chosen for historical reasons. And as you might guess, the person who chose it was Ronald Fisher. Ronald Fisher suggested 5%. He said, well, a 1 in 20 chance. What about that? And he even said that, that might be okay for some situations. There might be other situations where you might want to be more strict, like 1%. There should be a 1 in 100 chance. So that would be p equals 0.5 or p equals 0.1. And people, of course, have lit on this. They've kind of jumped on that, and that has effectively become set in stone historically since that point in time. But it is arbitrary, and we need to bear that in mind. Nobody ever wanted to be 93% sure about something. They chose 95%. He chose 5% because it's a nice round number. Again, it's totally arbitrary. So we're saying that if the probability is p.005 or greater, the convention is to accept the null hypothesis. We say that, well, there's a more than 1 in 20 chance that the null hypothesis is true, and that's big enough for me to accept it and say that the data, the evidence, the result supports the null hypothesis. Conversely, if it is less than this arbitrary figure of 0.05, the convention is that we reject the null hypothesis. We say that the data, the evidence is sufficiently rare, the evidence that we're getting occurs sufficiently rarely that we would say that we can't really support the null hypothesis, and the convention is to reject it. So that's the thinking behind it. But what we're not doing is, contrary to a lot of statistical teaching, the p-value does not indicate the probability that the null hypothesis is true, or the probability that the data were produced by random chance. As I keep saying, it's really about the data itself and how compatible or incompatible the data are with a null hypothesis. And I'm guilty of stating the probability of the null hypothesis true many times in various slide decks and even training courses I've written. And you'll see it all the way through textbooks. You'll see it all the way through software manuals and stuff like that. This is the probability the null hypothesis is true. This is the probability the data were produced by random chance. So we're in very good company. You'll see it all over the internet. You'll see this many times. It is correct. It is actually incorrect. What the p-value shows is, as I say, how many times you would get a result as extreme as the one you're seeing, assuming the null hypothesis is true. And if that seems like semantics, if you think, well, surely it's just the same thing, it isn't actually the same thing. And I'll show you why. The reason is simply because the probability of x given y is not the same as the probability of y given x. So if you say to yourself, for example, what's the probability of someone having a driving license given the fact that they're age 17 or over? That is not the same, of course, as saying, what's the probability of somebody being age 17 or over given that they have a driving license? Because the two group sizes are different. The number of people age 17 or over is probably larger than the number of people who have a driving license. And so therefore the proportions aren't the same. So in the same sense, the probability of null hypothesis being true given the evidence is not the same as the probability of getting that evidence, assuming the null hypothesis is true. And I understand that that is a difficult thing for people to get their head around, but really the point here is that there is a reason why we choose this form of words. It's a bit like in a court of law. In a court of law, we cannot help but assess a person, an accused person, on the basis of the evidence and say, well, what's the chance this guy is innocent? What's the chance that this guy is innocent given the fact he threatened somebody a week before they were killed? He bought a gun, 2 weeks before, and he was in the vicinity of the murder, an hour before it occurred. And then we think, well, what's the probability of that of him being innocent given that evidence? Versus what a statistician would do and say, well, what's the probability of you getting that evidence, assuming he's innocent? What's the probability he could have threatened the guy? Well, maybe he threatens people all the time, and maybe the guy's threatened all the time. What's the probability he would have bought a gun, 2 weeks? Well, maybe he buys guns all the time, or people buy guns all the time. And what's the probability that he would have been in the vicinity an hour before the murder occurred? Well, if there's 1,000 people in the vicinity an hour before the murder occurred, then there's a relatively high chance that he might be in that area. So it's a very different way of thinking, and it has important ramifications. So the null hypothesis itself is actually pretty important in these tests of significance, because that is what anchors our thinking. And to correctly interpret any significance test, you're going to need to know the null hypothesis associated with it. So there are lots of different types of significance tests, as I guess you're aware of, and they all have their own kind of null hypotheses. So let's have a look at some. So in a chi-square test, which we're going to see, the null hypothesis is that the two variables are independent of one another. They are not related. In a t-test or an f-test, it is that any differences in group means are just random, or just a sampling error, if you like. It's just an artifact of the sample. And in reality, the group means are the same in the population. They have the same value. In a Pearson's correlation, which we're going to look at in a moment, the null hypothesis is that in reality, the value you're observing, again, is just one of these sampling error situations, and that in reality, in the population, there is no relationship. There's no linear relationship between the two fields, the two factors. It's actually zero. And then you can get stuff for like Levene's test, where quality of variance is that the two groups have the same standard deviations, and the test for normally distributed data is that the variable is normally distributed. So you get this sense of every time you look up a statistical test, you have to say to yourself, well, what's the null hypothesis for that test? What am I actually testing? What am I actually assuming is true? So that's important. So if we look at an example here chi-square and crosstabs, because these kind of work together. Crosstabs are a powerful way to examine relationships between categories. So they're used for category fields. And here we have an example here, a screenshot from SPSS. We're looking at the relationship between gender and employment category. And if we run that, we'll get a little crosstab, a little table, which is simply tell us how many men and women fall into the different employment categories. And we're asking ourselves, well, you know, is it possible, or is there enough evidence to support that people's gender in no way affects their employment category, or that there's no relationship between the two, that they're actually completely independent of one another? And of course, if we do a crosstab, we get a table like this. And it says, okay, you got 206 clerical workers who are female, 157 who are male. You got 0 clerical workers custodial group, 27 male workers in the custodial group. You've got 10 female managers and 74 male managers. And this is from a data set which we've written about called the bank data set, an employee data set, which was actually used in a court case, where they used statistics actually, in inverted commas, to prove that there was discrimination within the employment of that bank. So of course it's very hard to compare these two groups because they're different group sizes. So we tend to use percentages. So we say 95% of the females are in clerical work, only 4.6% of the females are managers, compared to 60% of the males who are in clerical work, 10% of them in custodial, and 28% managers. Now it's entirely possible that the differences we're observing here, and they're quite marked differences, have occurred simply randomly due to the sample. And if we repeated the sample, you know, again, we might find that there's no difference. Okay, so what we have to do, of course, is we have to run, as we say, a test of significance. And the test of significance associated with crosstabs is called the chi-square test, and Carl Pearson came up with it. And the way in which a chi-square test works is very similar to flipping a coin and saying, I got 65 heads and 35 tails. What would I have expected to get? You know, and you know what you expect to get. You expect to get 50 heads and 50 tails. So in the same sense, the chi-square statistic is driven by what you got versus what you would expect to get if there was no sort of bias, if everything was evenly distributed. So it's looking at what's called the expected count. You can get crosstabs to display expected counts, and they're basically worked out by multiplying the row total for a cell by the column total for a cell, so 216 by 363 divided by the grand total, and that gives you the expected count. So if I multiply 216 by 363 and divide by 474, I get 165.4. It's saying that you got 206 female clerical workers. If everything was evenly distributed and adjusting for the sample sizes, etc., and different group sizes, you'd actually only expect to get 165 in there. So you're getting more than you expected, more female clerical workers than you would expect. And you can calculate these for all of the cells in the data set, and you get different expected frequencies. And the differences between the expected counts and the actual count, the actual delta, if you like, between them, so you can see a difference between 12.3 here and 0 is minus 12.3, is called the residual. And obviously, if you added up all those residuals, it would sum to 0. So what you tend to do is you square the number to get rid of the negative effect. So you square them. But basically, the sum of these residuals, the bigger that number is, the bigger the difference you're getting between what you observed and what you would expect to get if everything was fair and evenly distributed, and there was no difference effectively between the chance of a female being a manager or a male being a custodial worker or a clerical worker. And the larger that number, the less likely it is that the less evidence there is to support the null hypothesis. That number is called the Pearson chi-square statistic. And we perform a calculation which is based on the squared residuals, where we kind of sum them. It's a wee bit more involved than that, but not much more involved than that, where we kind of sum the squared of the residuals. And the larger the number, the less likely it is that the variables are unrelated to each other in the population. This value is used to calculate a Pearson chi-square statistic, which is down here. And you can see here that the significance, the p-value, is shown as asymptotic significance, two-sided. Two-sided just means it doesn't assume that there's any direction. Men are more likely to be managers than females, or females are more likely to be managers than males. It just assumes that it could go in either way. And the probability value here is less than 0.05. It's less than 0.01. It's actually off the scale. It's a very, very small number. So the null hypothesis associated with Pearson chi-square test is that the variables are unrelated. A small probability value of less than 0.05, according to convention, indicates that differences as large as the ones that we have observed will only occur quite rarely if we assume this null hypothesis is true. We therefore reject the null hypothesis. So if the form of words we're using is, the chi-square test indicates that the probability of obtaining a value as extreme as the one observed is less than 0.01, assuming the variables gender and employment category are unrelated. Given this result, there appears to be insufficient evidence to support the null hypothesis, and it is therefore rejected. Those are the magic form of words that you use that correctly interpret that significance test, if you like. So we're focused on the evidence. We're saying, how often would we get a value as big as that, assuming the null hypothesis is true? Okay, let's jump to a slightly different situation. Let's look at correlations and coefficients. And when is a significant result not that significant? Okay, so here's a scatter plot. So here's a scatter plot, and the scatter plot is really simple. It's showing a relationship between beginning salary and people's current salary from the same data set. And of course, what we find is that if you start on a big beginning salary, then your current salary is probably quite high as well, because if you start on $40,000, you'll end up on $80,000 or something like that on average a few years down the line. And people who start on on small salaries, it's not a random relationship between your beginning salary and your current salary. You can see that there's a sort of a relationship here, and it's shown in scatter plot. And we can measure other relationships in scatter plot. So here each dot is a car. Each dot, every single one of these dots is a little car. And it's showing the relationship here between vehicle, the weight of the car, and the horsepower. So heavier cars tend to have more horsepower. And here we have time to accelerate from 0 to 60 and miles per gallon. So if it takes longer to accelerate by 0 to 60, roughly it looks like you get more miles per gallon. And time to accelerate from 0 to 60 against horsepower, that's a negative relationship. It's saying that if it takes you longer to accelerate from 0 to 60, if it takes you like 20 seconds to get up to 60 miles an hour, then you probably have quite a small horsepower car, whereas a car with a lot of horsepower can get there in 10 seconds or something like that. And it turns out you can summarize this sort of relationship using these values, which are called Pearson correlation values. And the more extreme, if you like, the stronger the relationship, the closer they are to -1 or +1. So here we have a value here. This is a very strong one. This is quite close to +1. So it's 0.859. It's a very strong correlation. This is a wee bit weaker. You can see it's fuzzier. It's a weaker correlation value of 0.4. And this one's negative. This is going in the opposite direction. It's actually got a correlation value of -0.7. So they can't exceed +1 or -1. So a really strong correlation would be 0.9. A really weak correlation would be like 0.1. A really strong negative correlation would be like -0.9 or -0.85, something like that. And you can almost show these scatter plots to people and show them a few examples of correlation values, and they can guess the correlation just by glancing at the scatter plot really quite quickly. So they pick it up quite fast. Just to show you an example of what a completely random correlation looks like, what a random number situation is. This is miles per gallon against mileage, against the car's mileage. Well, of course, there's no relationship between the age of the car and the miles per gallon. And so the correlation is quite close to 0. It just happens to be a little bit under 0 here. It's effectively random. And the other thing I just want to point out is that, correlation values only pick up straight lines. So this correlation here that's showing -0.67, quite a strong negative correlation, but in fact, it can't see this curve. It only sees this straight line. So, it doesn't necessarily pick up relationships which are curvy linear. So there are some sort of limitations to it. That's why we talk about linear relationships as kind of straight line relationships we're looking at. Okay, so let's go and look at some real data now. So here's some data coming back to our employee data. This one's looking at the relationship between beginning salary and current salary and months since hire and previous experience and months. You could have been an executive who was just hired, a month ago. So there's no necessarily any relationship between your beginning salary and months since hire. Or your previous experience in months, you would kind of expect people to be more experienced to earn more, but that doesn't necessarily mean that, that doesn't necessarily always follow, because you might be starting a job as a caretaker there, and you might have, hundreds of months of experience, but it doesn't necessarily mean you're earning a lot. So that's probably more related to age than anything else. So I've just highlighted the stronger correlations here. Here's current salary, 0.880, and here's education level against current salary, 0.661. Here's education level against beginning salary, 0.633. The rest of the correlations, as we can see here, are quite weak. You know, this one's a little bit, this is education level against previous experience in months. It's saying that if you have more experience in months, you probably have lower education. It basically means that the older employees tended to have slightly less education. So we're looking at these relationships and we're saying these are very interesting correlations we're getting here, but which ones are, using the dreaded term, statistically significant? You know, maybe this is just a fluke. Maybe these are just, you know, if we did the sample again, we resample, we would get, you know, correlations of 0.08 as opposed to 0.8 here. So of course, when you run a correlation in tools like SPSS or SAS or R, what you'll get are these correlation values, but you often get the significance values as well. And we need to understand what the significance values are measuring. Well, you remember this, I said that the null hypothesis for Pearson's correlation is that the correlation value is actually 0 in the population. The null hypothesis is not that it's weak. You know, it's saying that it doesn't exist, that it's actually 0 in the population. So how big a correlation does it have to be for you to reject that null hypothesis? It's basically saying you don't have to be that big a correlation. So hence, when we run the correlation value and we add in the significance values, we can get situations where we have a very weak correlation here of minus 0.097, and the significance value is less than 0.05. And so it's statistically significant, but the correlation here is, you know, it's extremely weak. It's not really notable in that sense. Here we have a correlation that's very strong. The correlation value is easily less than 0.01, it's saying. So it's very, very unlikely. It's basically saying here that the likelihood of getting a result as extreme as that, assuming that there is no relationship between the beginning salary and current salary, is very unlikely. So we would reject the null hypothesis that the correlation is 0 in the population. Here it's very weak, and we're saying we're rejecting the null hypothesis the correlation is 0 in the population, but we're not saying that it's a strong correlation. We're just saying it's not 0. So is this statistically significant? Yes, because the probability of getting a result as extreme as minus 0.97, assuming there is no relationship between the two variables, is still only that should say 0.34. That should say 0.034 actually, not 0.34, so 3.4%. So it's less than 5, our magic 5%, but it's still very weak. Does that mean it's notable or worth reporting? No, not particularly. But then that's not what the null hypothesis for Pearson's correlation value is directed at. It only states that there's no relationship there at all in the population. So calling this statistically significant relationship, you can imagine somebody saying, oh, there's a statistically significant relationship between previous experience in months and current salary, and it'd be technically correct. But that doesn't mean it's notable. This is a classic example of when significant doesn't really mean significant. You know, you really should be looking at the actual differences, the actual strength of the relationship itself, and reporting on that and saying, by the way, the evidence shows, the calculation shows that assuming there is no relationship between these two factors, the likelihood of getting a result as extreme as the one we've got is, you know, p equals 0.01 or something like that. So we would reject that null hypothesis. Okay, in our last topic here, we're going to look at confidence intervals. And this is interesting because this is again another commonly misinterpreted sort of test of significance or inferential test. It's not formally a significance test, but certainly an inferential statistic. As we know, different samples from the same population vary. So we're seeing variability. Okay. If you repeat the survey or project, you won't get exactly the same results. Calculate a statistic and the results vary from one sample to the next. No statistical calculation can tell you what the actual value of a population parameter is. It's unknowable. We don't know the true mean age. And we're never going to have the luxury of repeating samples over and over again and try to get it right. But it turns out we can estimate a range of values that the population parameter is likely to lie within. And we do this by requesting confidence intervals. So confidence intervals can be shown graphically as error bars. These are these little bars here. They look like little TIE fighters, if you like. The value in the center here happens to be the mean, and the up top and the bottom indicate the confidence intervals. How confident, if you like, are we of the mean being within that range? So it turns out in tools like SPSS, there's various places you can get confidence intervals, but probably the most common one is the explore procedure. And it produces lots of summary measures. You can see, look at all these different descriptive statistics, 5% trim mean, standard deviation, minimum, maximum, range values, all these weird values here. But it also just happens to throw in confidence intervals for this mean age. Mean age in employee is 34.74. What is the true mean age in the population? 33.67, 35.80. It's saying there's a chance it's somewhere between there. So it's also providing confidence intervals. In this example, the mean age happens to be 34.74. Of course, we don't know what the mean age for employees is in the population that the sample was drawn from, but the confidence intervals indicate that it's likely to be contained in a range like 33.67 to 35.8. As we know, drawing another sample would result in a slightly different mean value. Okay. But all our statistics are likely to vary from one sample to the next, not just the mean. That's the thing to bear in mind. So if we drew another comparable sample and recalculated the confidence intervals, they too would probably be different. It's not just the mean that would shift, the confidence intervals themselves would shift. So in other words, we can't get too hung up on the values of the confidence intervals themselves any more than we can get fixated on the precise value of the mean. What we can say, however, is that even if the intervals vary from one sample to the next, they are likely to be broad enough that on 95% of occasions, they will contain the population mean, i.e. the parameter. What we should not say is that we are 95% confident that the population parameter is between X and X. That is the incorrect way to report that. And that's because, of course, the intervals themselves will vary from sample to sample. So we can't focus on X and X. And there's no scientific basis to the phrase we are 95% confident. Think about it, we wouldn't say we're 35% emotional or 73% optimistic. What does 95% confident mean? The true value is either within those intervals or it's not. The procedure that we use in the confidence interval procedure on 95% of occasions will capture the population mean. And to show you how prevalent misinterpretations of statistics are and how poorly, if you like, how poorly controlled some of the languages around that. If I skip out here to Google and just show you what happens when you Google correctly interpreting confidence intervals, the very first hit that comes up is from interpreting confidence intervals stat 200. The correct interpretation of the 95% confidence intervals is that we are 95% confident that the population parameter is between X and X. So it's perfectly understandable that people make these mistakes when you have, this sort of language that is being used so repeatedly throughout various textbooks and stuff like that. It's actually incorrect. Okay, so how are confidence intervals actually calculated? Well, it turns out that this is calculated or driven by a special statistic called a standard error. Okay, and it's one of these little statistics that people kind of hear, but they don't really pay a lot of attention to. When we calculate confidence intervals for a mean value, we use the standard error of the mean. But there are standard error statistics for lots of other statistical values, not just the standard error of the mean. You can get standard error of the median, standard error of the difference, standard error of the correlation. Standard error of a difference is what's used, for example, in a t-test. And these are useful for when we need to calculate confidence intervals, not just for averages like means, but for confidence intervals of percentages and of differences and correlations, etc. The standard error is based on standard deviation. We're taught what a standard deviation is in school. Standard deviation tells us what the average spread is, what the average deviation about the mean is within a sample. And just as a standard deviation measures variation within a sample, the standard error estimates variation between samples. It's telling us how much we would expect our mean to vary from one sample to the next. Here's our mean here of 34.74. It's saying based upon your sample size and the standard deviation, I would expect if you were to repeat this sample, on average, it would vary by about half a year, 0.542. So it's going to vary a little bit. And that allows us to calculate 95% confidence intervals. 95% confidence intervals are calculated by taking this number here and roughly doubling it, multiplying by 1.96. This is to do with normal distribution, this number of 1.96. But suffice to say, it's a pretty important number, that this 95% in statistics. That basically, if I take 0.542 and then multiply by 1.96, I get just over 1.062. And if I take that away from 34.74, I get 33.678, which is 33.67 here rounded up or truncated, and here 35.8. It's truncated here, 35.8. And that's how the confidence intervals are calculated. If I didn't multiply it by 1.096 and I just took it away and added it to the mean just as 0.52, I'd be actually calculating 68% confidence intervals. And if I wanted 99% confidence intervals, I'd actually triple it. I'd actually multiply it by roughly 3 and add it and take it away from these two values. So because the standard error is based on the standard deviation of sample size, the width of the confidence intervals is therefore affected by two values: the size of the sample and the spread of the data. So confidence intervals get further apart when the sample sizes are smaller, because you can't be as confident, and when you have a lot more spread, because that makes the standard deviations bigger, and that affects the standard error. The standard error gets bigger. So confidence intervals conversely move closer together. They get much narrower when you got a big sample and you don't have a big standard deviation. So those are the two things that affect it. Now, to illustrate it here, just in the last few minutes, and to show that confidence intervals themselves you don't really get hung up on, but the technique itself will, on 95% of occasions, capture, if you like, the true mean value. I've actually got some data here, and I'm simulating a population. This is a data set here. It's got 3 million cases in it. Okay, so 3 million cases, and let's assume that that's a population of a small country. We don't know what the true mean value is, okay? But if we're taking a sample from it, but let's say in this case we actually happen to know the true mean value. It's just that the researcher doesn't know the true mean value, and they've only got budget to do a sample of 50. So you wouldn't expect that a sample of 50 to be that close to the true mean value. Well, what happens is if I run confidence intervals and I run them 20 times on a random subset of 50 each time, it's going to calculate different confidence intervals each time. So the confidence intervals are going to shift from one to the next. And I've tried this out several times, and basically on average 19 times out of 20, it will capture the true mean value. And I can run this and you can see it counting through them if I just run this as it does this. So it runs up, there's the true mean value here, it's 3.33. So the first confidence interval comes up 2.33, 3.99, it captures it. It's within that zone, isn't it? Here's the second one, still within the zone, 231, 365, 287, 485. Let's see, there's a fourth one coming up, 378. It has to be, remember, it has to be 3.33 is the number we're focused on, still within it. Number 5, number 6, 6th done on a sample of 50. The 7th one done. Still 3.33, still within them. Let's see if one of these doesn't capture it. Still 3.3, still within 363, so it's still less than 3.3. 3.33 still less than that. Here's number 10, so we've got another 10 to go. Still capturing it. It is possible that all 20 will get it, or it's possible that 18 will get it, or 17 will get it, but on average, 19 will contain it, and 1 won't. That's why it's 95% confidence intervals. Okay, 3.33 still within that. Here's number 15, 15th sample coming up. 3.33 still within that. It is possible we'll get all of them on this occasion, let's say. 17. But you can see the confidence intervals themselves are shifting about the place. Let's see, the last 2 to go. Just squeezed in here, 3.33. And the last one itself. Okay, so it turned out on this occasion, randomly, on this occasion, it actually, all 20 of them managed to capture that overall population average of 3.33 from 3 million cases. Each time taking samples of 50, it actually managed to capture it. The samples but each time the confidence intervals themselves are shifting about. So that's why we can't say there's a 95% chance that the true value is between these 2 points, because the points themselves vary. So it's really that 95% of the time this method will capture the true value. I've done it several times. Sometimes it's come up with 18 times it's captured it and 2 times it hasn't, but generally speaking, on average, it's 19 times out of 20. In this case, it's actually got 20 out of 20. Okay, so graphing confidence intervals, error bars. Error bars are just a way to graph it. The dot in the middle here is showing from a sample. It represents the mean, but the upper and lower bars represent the upper and lower confidence intervals. Here we have females and males. Note that the bars don't quite cover the same range of values, and note that the bars overlap. So this is the mean age of employees by gender. And this is a bit like a significance test. We're saying that if we repeated our sample 100 times, that, you know, there's most times, on 95% of occasions, the mean ages for male and female would kind of fall within the same zone. Notice that the groups, the intervals are further apart for females than they are for males. There's only 2 things we know that can drive that. Either there's more variability in the age group for females, or that the female sample is smaller, or that the female sample is smaller. Look at this one though. Here we have clerical workers, custodial workers, and managers. Now, the clerical workers and managers overlap. It doesn't look like, if you repeated the sample 100 times, 95% of the times you'd get means where clerical workers and managers were kind of in the same zone. So that means that there's a pretty good chance that in reality they're the same age. But we can see that the custodial workers are well outside this zone. So it's almost like we're saying that they are significantly, if you want to use a term, significantly older than clerical workers or managers. And again, the bars are further apart, and that's either because or because there's just more spread in the custodial group, or because the custodial group is smaller. Okay, just a few things to finish up on in the last minute here. So further reading. We have I've written a series of blogs called the Eat Your Green series. And the Eat Your Green series is really about going back to the basics of statistics. They kind of go through it in sequential order. And here, when you get your PDF, you'll be able to click on these. It will take you to that particular web page, that blog. So it looks at things like why is something statistically significant, not always practically significant, and what makes a standard deviation standard, and why is normality so important, normal distribution, and understanding correlation, making sense of significance tests, right up to things like something called power analysis, because that's been introduced into SPSS recently. And the other thing to bear in mind is that a lot of this has been inspired by David Spiegelhalter's last book, which is The Art of Statistics. Spiegelhalter's been very present on the media recently, particularly talking about COVID and the government's response to COVID and how we measure efficacy and how we make sense. This is a very good book on the art of statistics, and it really cuts through a lot of the noise and sets you straight about, this is actually how you interpret significance tests, and this is what 95% confidence intervals mean. Very good book. We also provide our own ebooks that you can download for free. So we have stuff that looks at things like predictive analytics projects, which you can download for free, but we also have stuff, introduction to machine learning and customer analytics and that sort of stuff. And we're running an offer at the moment for our various online training courses. We have a lot of online training courses. Some of these are self-guided courses, the recorded courses or materials you can download. If you want to check them out, then you should be aware that we've got a 50% off all of our online self-paced training courses before the 12th of February. And lastly, with regard to working with us, we can source software, so we can buy your analytical software, and you can get that directly from us, particularly if you're looking at SPSS software, and we'll help with the selection and piloting of implementation of analytical tools. We also provide a number of different training services, things like online training. So we've got a bunch of online training courses that we're providing coming up in the next few months, obviously because classroom training is not really appropriate at the moment. And we'll even help with the identification and recruitment of analytical skills into your organization. We are an official support providing partner to IBM, so we will offer technical support advice for SPSS users if they're a customer for us, and we offer that formally, but we generally offer no strings attached technical and business advice relating to analytical activities. So you can drop us an email and we will do our best to help out. I do hope you found that useful. We will be rerunning this session next week to deal with demand, because we have quite a lot of high demand for it. And if you want to find out about forthcoming webinars, by all means, check out our website. We usually have a list of webinars that are coming up, and we also have recordings of old webinars that you can listen to as well. Thanks very much, and we look forward to you tuning in again.